So class, what is heat? Ah, got you there. All right, it's one of those things that you know what it is, but to define it is kind of hard. Okay, but we can do it in science, because with science we can do a lot of things. All right, so actually heat is a form of energy. Okay, it's energy that always goes from object at high temperatures to lower temperatures. Okay, so that's the way it goes. It can be transferred in three basic ways. First one, heat transfer is by conduction. Okay, so if you just take your hand and touch something, anything by direct contact would be conduction. Okay, so grab the desk, okay, grab the metal here, okay, you feel, it feels cold, okay, so things that are good conductors would feel cold as taking heat from your body. I grab this piece of clay, it doesn't quite feel as cold because it's not as good a conductor. Okay. So, right, class, conduction is heat transfer by direct contact. Okay, so I have two substances here. One is wood here, the other is iron over here. So the question to you is, if I place an ice cube on there, okay, on each of those, which will melt quicker? The wood or the iron? Which will melt the ice cube quicker? All right, make your guess. Here we go. Make sure it stays on there. So I'm not sure if you guys said the wood or the iron, but it's pretty evident that the iron or the metal is melting the ice cube quicker than the wood. Okay, and that's kind of the discrepant thing, is that metal feels colder than wood does. So you think, okay, well, wood would melt it quicker. Okay, but the reason that the ice cube is melting is because metal is a good conductor of heat, energy, whereas wood is a much poorer conductor, right? So this heat is being drawn out, okay, of the ice cube quicker than on the wood, right? So we could watch ice melt. Conduction. Next one is convection. Convection is a movement of fluids, and in science they consider fluid as anything that flows, so a liquid or a gas. Of course, it's responsible for a lot of weather patterns. So the sunlight comes down, heats the earth up, and warm air rises, and then cold air will drop back down. Okay, circulation patterns. Same thing happens in the oceans. Right, so cold water will sink down, and warm water will come back up and creates convection patterns in the oceans. Okay, so that's the second way. Convection is the movement of heat energy by movement of a fluid, which can be either a liquid or gas in a scientific sense. Okay, so if I light this candle on fire, here we go, get it lit up there. If I place this tube over the top, what do you predict will happen? All right, make your quick prediction. I'll put this over the top. 10, 9, 8, 7, 6, 5. It goes out relatively quickly because, of course, it runs out of oxygen. All right? So now, what I'm going to do this time, I'm just going to take this little piece of foil, place it down in here, like that. Okay? We're going to do the same thing. And now let's see what happens. Light the candle on fire. Now, just place this over the top again. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right, well, what's going on here? feeling over the top. This side over here feels warm. This side over here feels cooler. Okay, so what's going on inside is, of course, the candle's burning. It needs oxygen, and as it burns, warm air rises. By convection, its heat's transferred up. It's going along this side, so warm air comes up, okay, and that creates a lower pressure down there, so cold air is coming down. So you got this circulation, okay? So oxygen is continually being supplied from this side, and the warm air is leaving this side, so that candle will remain on as long as it's got fuel. Okay? And the third way is by electromagnetic radiation. Electromagnetic waves. All right? So we're being bombarded by radiation all the time. Of course, the sun gives off radiation, but there's gamma rays, there's X-rays, there's ultraviolet rays, visible rays, infrared, which is heat rays, heat waves, and radio. Okay, but that's a way in which energy can be transferred. Okay, so heat or infrared can be transferred that way. The third type of heat transfer is by radiation. So here I have actually a ultraviolet light. Okay, so of course radiation is all sorts of it. You have gamma rays, X-rays, ultraviolet rays, and this is a UV lamp. You have light rays, you have infrared or heat waves, and you also have radio waves. All right. So if I plug this in, it's giving off radiation. Okay, and mostly UV, but I just feel here, you can see lights coming off. If I just put my hand right here, I can feel heat. Okay, if this was an infrared bulb, it would be more heat, but it's giving off this ultraviolet radiation. Actually, I once had a student thought this was a regular light, used it for an experiment, and actually get sunburn because of the ultraviolet radiation. But I can feel that heat coming off here because the energy, the heat transfer is going right from the lamp to my hand. Okay, so that's by radiation. Okay, a good conductor, okay, transfers heat very easily. Okay, and then insulators are things which prevent heat transfer. Okay, so you're going to be doing some stuff with that this week in your lab. Okay, so you want to find some good insulators. All right. So that brings us into this concept of thermal energy. How much thermal energy something has. Okay, doesn't just depend on what its temperature is. Okay, it depends on three things. Okay, so mass, specific heat, and temperature. Okay, since everything always has a temperature, we're always going to be relative, so it's going to be a change in temperature. Okay, so the formula for figuring out thermal energy changes is Q. That's the symbol for thermal energy. Okay, Q equals mass times specific heat times the change in temperature. All right. Okay, so mass is important, right? So for example, I got see, I got a little dropper here. Let's just pretend that this was boiling hot water. Okay, now let's say I had one drop of it here. Okay, and here I had, let's say, 90-degree water. Okay, so in Fahrenheit, this would be 212 degrees, and this would be about 200 degrees. Well, of course, this one has a lower temperature than this, but if I asked you, ask someone, you want a drop of 100 degrees Celsius water on your head, or do you want, okay, this much 90-degree water on your head? Of course, this has more energy in it, so that would cause, okay, more burns, right? Okay, so that's the component of mass. The next one is specific heat. All right, so specific heat, sometimes it's called heat content. That's how much energy a substance can hold. Okay, technically, it's the energy you need to raise 1 gram of a substance by 1 degree Celsius. All right, so if I just took 1 milliliter of water, okay, or 1 gram of water, which is the same thing, and if I raise that 1 degree Celsius, okay, then that is its specific heat. Okay. Now in joules, you can see on the table that I'm hopefully showing you now, water has a specific heat when it's a liquid of 4,180 joules. Okay. versus something like aluminum or metals. Let's go, aluminum is 0.89 joules per gram degree Celsius, or copper is even lower, it's 0.385, okay, so less than 1, okay, for its specific heat, okay. So water actually has a relatively high specific heat, so it holds water really well, okay, so that's responsible for a lot of properties, okay. Number one, you are mostly water. You probably heard you're like 60%, 63% water. Okay, so when you go out in the sun on a hot day, okay, because you have so much water, it takes a lot of energy to heat you up, so you don't overheat. Okay. We live on the west coast of the United States, okay, and we have that ocean just to the west of us, which acts as a great moderator of temperature. Okay, so in the summertime, especially if you're at the coast, the sunlight, that energy is absorbed by the water, because water has a high heat content or high specific heat. It takes a lot of energy to heat it up, okay, so it absorbs that heat, which means it doesn't get quite so hot inland. In the winter, the opposite happens though. When you don't have as much energy from the sun, okay, the water can give off heat, okay, so in the winter time, the coast is actually a little bit warmer than inland because of this moderating effect of water because of its high specific heat. Okay. Then finally, of course, temperature. Okay. Remember, temperature is actually how fast molecules move. We measure with the thermometer. Okay, so right here in this room it's 20 degrees. Okay, if I was to put my hand, I'm 37 degrees because I'm human. I mean, I think I am, but I am human. Right, so if I put my finger on the bulb here, okay, what am I doing? I'm transferring my heat by direct conduction, so this is conduction. Okay, but it's getting into that, transferring to the liquid inside, which is actually, it's kind of a red dyed alcohol inside, and it's going up, okay, so it's going up, it's around 26 degrees there now. What actually is happening in those little molecules, they're actually moving faster, and as they move faster, they increase in volume, okay, and that's how a thermometer works, okay. But that's a component of thermal energy, okay. So if you want to get the energy changes, you can measure mass, specific heat, and in the change in temperature, you can see how much thermal energy has been absorbed or lost.